welcome back to the deep dive. If you thought modern warfare was all about what happens inside the cockpit, this deep dive is, well, it's going to fundamentally change your perspective.
It really is.
We are looking at a military concept that argues the most dangerous threat to our forces isn't a new missile or a stealth fighter.
No.
It's a procedural document. It's the rigid, static, and frankly outdated way we manage airspace.
Yeah. We're going deep into a proposal to shift control of the military sky from what is essentially a slow, fallible human bureaucracy
Mm.
to dynamic, real-time algorithmic integration.
And this is a truly radical paper. It feels like it's diagnosing a sickness that has been slowly, debilitating joint military operations for decades, really since the Cold War.
That's a great way to put it. We're exploring this concept laid out by M.A.J. Andrew Pingree, and he calls for dynamic algorithmic integration. And this isn't just, a simple tech upgrade.
No, it's a whole philosophy shift.
It's a necessary strategic shift to survive, especially when you're talking about facing highly capable, peer-level adversaries. Think about places like the Korean Peninsula or the contested environments of Eastern Europe.
Absolutely. The mission here in the source material is very direct about this, is straightforward but aggressive. It says we must dismantle what the author calls the procedural anchor.
And that anchor, it's the heavy, centralized weight of these static airspace coordination measures, or ACMs. It's the whole cumbersome clearance process that dictates how every single fighter jet, every drone, every artillery shell uses the air.
So we really have to ask, why is this change so urgent right now?
Well, for decades, the U.S. and its allies, we operated in what you could call a positive control era.
We own the sky.
We owned the sky. We had total air superiority, low risk, and the luxury of time for slow manual coordination. But, you know as well as I do, those days are just over.
They're gone.
The current models, which all rely on centralized planning and a human somewhere checking a box, they cannot possibly keep up with the speed and complexity of modern threats.
We're not just talking about another fighter jet here.
No, we're talking about hypersonic warfare. We're talking about massed, swarming drone attacks and constant, debilitating electromagnetic contestation. Jamming.
And this is where we get to the truly shocking claim that this entire concept really pivots on. In a peer-level combat environment, these static, centralized procedures don't just create friction, they don't just slow you down.
No, they create fatal signatures.
Exactly. The paper argues that the very act of following the rules that were built for peacetime safety makes us strategically vulnerable. It paints a target on our backs.
It forces this really difficult realization that our traditional way of achieving safety, which is, making sure a single authority grants permission for everything, is now an active liability.
So the whole concept is built on decoupling safety from centralization.
That's it. And that is the critical break from tradition that staff officers who grew up relying on positive control find so incredibly difficult to accept. It's a cultural shock.
Okay, let's unpack this, starting with the problems of the old way. Because to really understand the solution, you have to appreciate the depth of the structural failure that's been created by that procedural anchor.
What stands out immediately is just how thoroughly this concept analyzes the traps we've set for ourselves. It's not just a technological limitation, it's deeply rooted in human cognitive limits and bureaucratic lag. The paper calls them the cognitive and temporal traps.
Right. And the temporal trap is the easiest one to grasp.
Yeah.
If your centralized control process, like, let's say, drawing up restrictive boxes on a map, like joint fires areas or JFAs, if that takes 4, maybe 6 hours to approve and then publish to the force,
then that plan is already stale the second it's released. It's creating this massive temporal lag that a modern battlefield, which can shift completely minute by minute, it just can't sustain that.
and that time lag leads directly into the core cognitive limitation, what the author calls the pilot as data processor.
Yes. In the existing paradigm, the pilot, or, their remote drone operator, isn't just flying. They are acting as the primary high-stress fusion engine for airspace safety.
They're the final firewall against a mistake.
They are. They have to manage enemy threats, execute their own mission, watch their fuel, and on top of all that, constantly cross-reference their current position against a ground picture that is, by its very nature, outdated.
And how do they even get that outdated picture? I mean, this is where the liaison disconnect comes in.
Exactly. They're relying on ground liaison officers, GLOs. And these are vital human staff, of course, but they are processing data that by the time it reaches the pilot in a pre-flight brief, might already be hours and hours old.
So if an enemy mechanized unit successfully pushes forward their positions by 5 kilometers while that brief is being printed,
The pilot is flying with fundamentally inaccurate data. A planned safe corridor could now be right over a new enemy air defense system.
and this leads right into the retention gap, which I found fascinating.
It's just brutal when you think about it. Imagine you are a highly stressed pilot or even a remote operator in a ground station. The paper states you absorb maybe 30 to 60% of a complex pre-flight operational brief.
And these briefs are not simple.
Oh no. They're often filled with pages of coordinates for static no-fly zones, ingress corridors, egress corridors, coordination points. It's a massive data dump.
And then, 6 hours into the mission, you're deep in contested territory, and someone comes over the radio and says the whole tactical situation has changed.
Right, and you, the pilot, are asked to mentally update this huge database of static information in your head. I mean, it is physically impossible for the human mind to process and retain that volume of nuance under that kind of duress.
So we recognize this was a problem, and our solution for years has been what the paper calls the cockpit fallacy.
Ah, yes, the classic military solution to a data deficit problem.
Just push more screens.
Exactly. Throw more text, more graphics, more maps into the pilot's field of view. We'll solve it with more data.
Which fundamentally confuses data delivery with actual knowledge acquisition.
It does. Adding more digital maps or more warning chimes or another text list of JFA coordinates, it just increases the pilot's cognitive load without actually improving their situational awareness.
It's just noise at that point.
It's just noise. A ground commander in a tactical operations center, a TOC, they can spend hours analyzing the fine print on a common operating picture. A pilot has milliseconds to make a life-or-death decision while pulling 7Gs.
So by throwing raw data at them, you're turning them into a glorified data processor.
And you're severely degrading their ability to be what they're trained to be, a high-level tactical decision maker.
So the human is the bottleneck. And this structural bottleneck is formalized by what the paper calls the latency anchor, which they simplify brilliantly with the BBC broadcast model.
This analogy is just perfect for illustrating the rigidity of the Airspace Control Order, the ACO. The ACO, as it's done today, is a single monolithic signal. It's issued by a central authority, the Combined Air Operations Center, or CAOC.
So it functions like a World War II radio broadcast.
That's the image. This is London calling, and here is the definitive, unchangeable plan for the next 12 hours.
And because it's a central, monolithic document, it has to be approved, written, formatted, and then disseminated, which means, by its very definition, it's static. It's versioned.
Precisely. You might be out there executing ACO version 1.2, but the enemy's operational tempo is already at version 4.0. The CAOC staff might be brilliant, but they are writing a document that takes hours to get to the force.
But the threats swarming drones, maneuver warfare, hypersonic missiles, they require updates in seconds, not hours.
So the plan is instantly obsolete the moment it's published.
And this structural rigidity is also paired with an extreme fragility.
Yes. Relying on a centralized ACO assumes a permissive environment. It assumes that central CAOC can maintain this God's eye view and push the signal out reliably.
An assumption you absolutely cannot make in a peer conflict.
Not at all. The electromagnetic spectrum will be heavily contested, jammed, or just flat out denied. So if that central radio link breaks, or if the CAOC itself is targeted and taken offline, the entire force is left executing a stale, static plan.
Based on a document that is now hours old and dangerously wrong.
That single point of authority and that single point of communication, it's not a control mechanism anymore. It's a strategic vulnerability.
So if you connect all these dots, the central problem is that we are prioritizing an easily identifiable, centralized point of truth in an age that demands distributed, agile combat.
We've built a system that's optimized for creating order in a low-risk environment, and that very optimization has now become our Achilles heel and a high-risk one.
It really raises a critical question. If your command and control system is designed to break the moment it gets contested, how can you possibly expect to dominate the fight?
You can't. You're losing the fight before the first shot is even fired because your planning cycle is just too slow.
And that structural weakness brings us directly into the tactical reality that's laid out in Section 2, the signature liability. Our static procedures don't just slow us down, they actually provide the enemy with a highly accurate map of our intentions.
And this, for me, is the most frightening element of the entire paper. It's the pattern of life that's generated by our own procedural rigidity.
It's a self-inflicted wound.
It is. We are so constrained by our own rules, the lines we draw on the map, that our behavior becomes dangerously predictable. The enemy doesn't need to employ sophisticated cyber warfare to break our
They
encryption.
just need to sit back and watch.
Just sit back and observe our compliance with our own predictable static coordination measures.
This sounds exactly like reverse engineering our own doctrine.
That's what it is, and it's what AI and machine learning are perfectly designed to do. An AI-enabled adversary can fuse multi-source intelligence, SIGINT, radar tracks, visual observation from drones, and it can look for patterns. But critically, it can also look for the negative space.
Okay, you have to define negative space in this context. What does that mean?
Negative space is the area we don't fly in, or the specific times we don't fly in certain corridors. It's the void that our rules create.
Can you give me an example?
Sure. Let's say U.S. Army doctrine procedurally anchors its helicopters to operate strictly below 1,500 feet after or 300 hours. And at the same time, Air Force jets must ingress a target area above 20,000 feet.
Yeah.
An enemy AI immediately knows that the massive chunk of airspace between 1,500 and 20,000 feet is procedurally free. It might be empty because we designated it as a Joint Fire Area Keepout, a JFA. The enemy doesn't just see empty airspace. They see a deliberately reserved, rigid, and predictable operational box.
Here's where it gets really interesting. The enemy is using our own rulebook against us. If we are that predictable, that predictability allows for predictive targeting.
Absolutely. An enemy AI can deconstruct our airspace coordination measure, our ACMs, just by monitoring our flight paths over a few days. By knowing where we are not going or where we must turn to stay inside procedural box. They can identify the specific, rigid ingress and egress corridors we are forced to use over and over again.
And what kind of information does that predictability really give an adversary? What can they do with that?
It allows them to locate critical infrastructure without ever seeing it directly. If they know the only safe flight corridor for our logistics helicopters runs along a specific river valley between 0400 and 0600 every morning.
They know exactly where and when to put their anti-aircraft assets.
Exactly. They can dedicate their ISR and their targeting assets to that specific time and place. They can start to locate our artillery positioning areas, our command posts, because they can see where all the coordination boundaries converge. And they can predict our likely strike vectors long before we even commit a weapon to the target.
So our procedural control is literally an open book. It's a blueprint that exposes all the seams between friendly units who are just trying to deconflict from one another.
It absolutely is. And this confirms a really crucial observation from General Donahue, which the paper cites. He said that the modern fight is fundamentally a fight between staffs.
Not just a fight between jets.
It's not just platform versus platform anymore, not just an F-35 versus an enemy fighter. It's the speed and the agility of one staff's planning cycle versus the others.
And if our staff is relying on static, predictable procedures,
they lose the planning fight every single time against a staff that can exploit dynamic patterns using AI.
I really see the gravity of that now. This isn't just about a little bit of tactical friction. This shifts the entire focus of the battle from who has the best hardware to who has the fastest processing speed and the most information agility.
Right. Our existing control mechanism is actively eroding our agility.
The conclusion seems undeniable. The current system forces commanders to control the airspace. But in doing so, they sacrifice the ability to actually dominate the fight.
Domination requires decentralization and speed, the two things our current system is designed to prevent.
So if centralization and procedural rigidity are the disease, what's the cure? How do you build a system that is fast, safe, and distributed? This moves us right into Section 3, the new paradigm. And this is a big shift from control as a human procedure to control as a network-centric service.
This is the critical conceptual leap in the paper. It proposes moving away from a human-centric procedure that, requires asking for permission and replacing it with a service that provides immediate algorithmic risk calculation.
And they term this the VFR philosophy, or digital visual flight rules.
Right. And it involves applying the logic of something we all do every day, driving a car, to the combat pilot. The automotive model is really key to understanding this transition.
It's the most accessible analogy, for sure.
It is. Think about your daily commute. Google Maps or Waze, that's the centralized control. It provides you with the optimal plan based on the best available, but still kind of stale data it has.
But the moment I, the driver, the edge sensor, see a car run a red light or suddenly swerve into my lane,
you react immediately. You slam on the brakes. You don't wait for the Google satellite to confirm the accident, process the incident, and then send you a new route update a minute later.
right, but then it's too late.
So the aircraft, the missile, the drone, they become the drivers. They use their own onboard sensors and a local mesh network to instantaneously negotiate airspace geometry in real time. And they do it independently of that centralized, slow airspace control order.
This is edge decision-making. It fundamentally changes the role of the pilot.
It does. It means the system handles the geometry, the pure math of collision avoidance and friendly fire deconfliction, while the human pilot, or the platform's AI agent, handles the intent. They handle the mission itself.
And that distinction is just paramount. It directly addresses that cognitive load problem we were just talking about.
Yeah.
The pilot only has to focus on the why of the mission, not the how of the geometry.
Exactly. The system transitions the entire joint force from what is essentially a permission-seeking bureaucracy into a self-synchronizing ecosystem.
So the pilot just states their intent.
Right. The pilot says, I need to drop this ordnance on target X in the next 5 minutes. The mission computer then calculates the risk high, medium, low based on that exact moment's dynamic threats, friendly unit locations, potential artillery trajectories, all of it.
And it presents the pilot with an optimized, safe path without them needing to call someone for approval. But I have to ask the obvious question here. Doesn't this seem inherently more dangerous? We're taking a human who is trained for years to look for risk out of the loop and replacing them with a computer that's just calculating probability.
And that is the huge cultural hurdle. But we have to weigh the risk of the highly reliable algorithm against the known risk of the fallible, stressed human who is relying on stale data.
So it's a different kind of risk calculation.
It is. The algorithm doesn't make errors reading coordinates, it doesn't get tired, and it operates in milliseconds. The current system introduces massive, unquantifiable risk because of the human element and the data latency. The dynamic integration concept proposes that actuarial security, the statistical reliability of the algorithm, is far superior to the illusion of positive control, which is just a human signing off on an outdated plan.
That makes a lot of sense when you frame it that way. The system doesn't need to ask for permission if it can reliably calculate and mitigate risk faster than any human staff could possibly respond.
But if we're going to abandon the static corridors, the guardrails, we need an incredibly robust technical backbone to maintain that safety.
Which brings us to Section 4. To make this all work, you need a rigorous digital chain of accountability. Okay, this is where we really stop thinking about lines on a map and start thinking about a true digital ecosystem. To replace those static corridors, the concept requires a comprehensive telemetric chain of custody.
Essentially, this is the Internet of Military Things, or IOMT, deployed in the most kinetic environment you can imagine.
So every object in the airspace has to be a persistent, traceable node on the network.
Every object. This
Wow.
can't be limited to just the major platforms like F-35s and B-21s. It has to include every tactical system. Loitering munitions, small reconnaissance drones, rocket systems, and even specific types of guided artillery shells.
And for any of the non-ballistic systems, anything that can maneuver, the paper requires them to continuously broadcast their 5Ws. What are the critical elements of that data stream?
Okay, so they are constantly securely transmitting who they are, their unit and platform identification. What they are doing, their current flight parameters, speed, altitude, where they are, their precise GPS location, when they will be at their next checkpoint, and maybe the most critical variable, why their mission priority.
I want to focus on that mission priority for a second.
Yeah.
How does the network use that why to deconflict everything?
That becomes the core decision matrix for the machine-to-machine negotiation. So imagine two friendly platforms are converging on the same airspace.
Yep.
One is a critical close air support asset, a CAS jet, and it's needed to save ground forces who are taking fire. It's broadcasting a mission priority of high. The other platform is a routine intelligence, surveillance, and reconnaissance drone, an ISR drone, and it's just flying a standard pattern, broadcasting medium-low.
So they're on a collision course.
Their edge computers calculate a geometry conflict. The algorithm automatically prioritizes the CAS asset with the high priority and instantly reroutes the ISR drone. Maybe it forces the drone to temporarily accept a slightly higher threat risk, or just divert a kilometer to the north.
And this is all happening without a human in the loop.
It's instantaneous and machine-driven. It ensures that the most vital mission is never delayed by procedural bureaucracy.
That level of dynamic prioritization is the complete opposite of the current system, where, a slow-moving, low-priority transport plane might procedurally shut down an entire ingress route for a high-priority strike package.
Exactly. But then we run into the dumb munition problem. The paper calls it the ballistic handoff. What about unguided artillery shells or unguided rockets? They can't communicate. They don't have a computer chip sending out the 5Ws.
Right. How does this sophisticated dynamic network account for a dumb 155 millimeter howitzer round that can't talk?
Since the munition itself can't talk, the launcher acts as its proxy. The moment a HIMARS system, or a 155 millimeter howitzer, or a guided rocket launcher fires, the firing platform immediately injects the precise ballistic trajectory of that round into the network.
And this is more than just a radio call saying splash.
Oh, much more. I need you to understand what's being injected here. It's highly technical data. The platform injects the projectile type and weight, the propellant charge amount, the precise muzzle velocity, which, varies with barrel temperature and wear, and the target coordinates.
So the network can compute the full trajectory parabola.
The full exact parabola, and this immediately creates a temporary, precise, virtual cylinder of danger in the digital airspace model. We're not talking about a huge box. We're talking about a cylinder maybe 5 meters wide and exactly as long as the round's time of flight, which is often less than 60 seconds.
So instead of shutting down a 10 by 10 kilometer block of air for 2 hours for safety, the artillery battery only digitally restricts this tiny, highly precise column of air for 1 minute.
That is the crucial game-changing benefit. Every friendly aircraft system in that area instantly receives this digital warning. The aircraft's mission computer sees the digital cylinder, calculates the geometry, and either adjusts its flight path by a few dozen meters or tells the pilot to wait precisely 60 seconds before proceeding.
All without a single human coordination call or waiting for a CAOC update.
It sounds like the ultimate realization of that old Air Force doctrine: plan centralized, execute decentralized. The commander provides the strategic intent, but the actual route to the target is no longer a rigid blue line on a map.
It's a fluid calculation based on this real-time mesh of threats and friendly fire.
And that enables machine-to-machine deconfliction in its purest form. Consider an F-35 and a friendly cruise missile converging on a target from different directions.
Under the old system, that's a nightmare for an AWACS operator.
A frantic nightmare trying to get them on the radio. Here, the two platforms communicate directly, in milliseconds. The aircraft's computer executes the reroute based on pre-programmed logic, something like, the missile is high priority and cannot deviate, therefore I must adjust my altitude by 500 feet immediately. The whole negotiation happens faster than a human can even register the threat.
That agility just drastically changes the tactical landscape. The pilot is completely freed up to focus on defeating the enemy, knowing that the geometry, the friendly fire problem, is handled by an instantaneous decentralized system.
The human is finally leveraging the machine's speed rather than being constrained by the machine's complexity.
Let's scale this up, though. The technical mechanics are impressive, but scaling this for a massive joint and coalition operation requires radical changes to communication and logistics. And that brings us to Section 5, where the paper stresses the need to banish the God's eye view mentality.
Yes. The traditional hub-and-spoke communication model, relying on one single large radar station or a single satellite feed, that God's eye view, is a massive liability that peer adversaries will target relentlessly on day one of a conflict.
So for dynamic integration to actually work, you have to adopt a robust mesh network architecture. It's all about data resilience.
And resilience in this context really means the diverse path approach. The data has to be platform agnostic. It cannot rely on a single radio frequency or a single communication source.
So the telemetry data about that friendly HIMARS launch we talked about, it has to reach an F-35 through any available channel.
Any and every available channel. That could be link 16, a heavily encrypted 5G cellular link that's been set up by a forward operating base, a dedicated satellite channel, or even a laser link that's bounced off a nearby loitering munition that's acting as a temporary repeater.
The platform just demands the data, and the network is designed to route it through the fastest, most survivable channel available at that exact moment.
Precisely. And this massive volume of diverse data streams is synthesized, but, and this is crucial, it's fused at the edge. It's fused inside the aircraft's computer without overwhelming the pilot.
This is the anti-cockpit fallacy.
It is. The system displays very little raw data. It's not going to show the pilot the dozens of inputs or the complex telemetry streams that it's processing.
So what does the pilot actually see on their screen?
They see a dynamically generated steer-to-cue, It's often a simple green flight path projected onto their display that navigates them through this complex environment of red enemy threats and blue friendly fire cylinders.
And the pilot does not need to know why that path just shifted to the left.
They don't. They don't need to know whether it was because a friendly artillery unit started a suppressive fire mission or because a new enemy air defense system just turned on its radar. They only need to know that the machine has calculated the safest, fastest way forward, and it did it instantaneously.
That simplicity for the human hides an immense amount of machine complexity. And this dynamic path generation achieves a critical tactical objective: survivability through chaos.
Absolutely. If every aircraft and every munition is dynamically calculating its path based on real-time data, you generate no repeatable signature for the enemy. There is no standard corridor. There is no predictable altitude band.
You're forcing the enemy's AI to target an unpredictable swarm, not an orderly, predictable procession.
And that's how you get chaos for the adversary, but controlled, safe execution for the friendly force.
It completely defeats the enemy's ability to engage in that predictive targeting we were so worried about. If the flight path of an attack aircraft is decided microseconds before execution based on live sensor data, the enemy cannot set an ambush. They can't pre-position their air defenses.
They're always a step behind.
Now, let's address the massive political and logistical headache that procedural control creates, and that's coalition integration. Our alliances, particularly in Europe or Korea, they rely heavily on rigid procedural agreements, which sounds like the heaviest procedural anchor of all.
Oh, it is. That's the JFAK problem, writ large. Alliance structures typically enforce these arbitrary spatial divisions just for safety. You know, the U.S. Army owns the air below 15,000 feet, the ROK Air Force owns everything above 20,000 feet, and there's a 5,000-foot buffer in between that nobody can use.
Which result in these massive volumes of what the paper calls holes in the water airspace that's technically empty, but is procedurally reserved and unusable for anyone.
It's incredibly inefficient. It severely inhibits maneuver.
So dynamic integration demands technical interoperability above procedural agreement.
It shifts the entire burden of coalition warfare. Instead of spending months in meetings negotiating rigid coordination protocols on paper, we have to focus on ensuring that a Korean K-9 Thunder artillery system can share a common, verifiable data standard with a U.S. F-35.
You're replacing fragile political agreements with robust, cryptographically verified data sharing.
If the ROK forces inject their ballistic cylinders into the network correctly, the U.S. aircraft can operate safely right alongside them. It's technology forcing unity of effort.
And the practical payoff is just efficiency and saturation. Procedural control causes so much waste. Long flight routes, constant holding patterns, delayed fire missions while we wait for some centralized deconfliction.
Dynamic deconfliction allows for saturation of the battle space, and that is the ultimate goal. You gain the ability to fly missiles through friendly artillery barrages and aircraft under rocket trajectories because the geometry is all calculated and maintained in real time.
So you can achieve far more effects out of the same number of platforms.
You're eliminating all that time spent just orbiting or diverting because of stale procedural rules.
That is a staggering jump in operational efficiency. But if we're moving all this decision-making from centralized humans to decentralized machines, we have to address the fundamental fears of chaos and failure. And that brings us to Section 6.
Right. And we have to acknowledge the critical and often skeptical arguments that come up. Critics of this idea, they fear that abandoning procedural control invites two potentially catastrophic failure modes.
The blackout scenario and the spoof scenario.
Network collapse and cyber intrusion. Exactly.
Okay, let's tackle the blackout scenario first. We're relying on this resilient mesh network. But what happens when a capable adversary successfully jams or destroys critical nodes, leaving our aircraft flying blind in a congested, dangerous environment?
The system is designed to mirror those digital VFR principles precisely for this situation. If the tactical mesh network, your Google Maps satellite feed, if that fails, the platform immediately defaults to independent onboard sensing.
The driver looking out the window.
The driver looking out the window. The aircraft must rely solely on its organic sensors, its own radar, its IRST, its LiDAR for immediate local collision avoidance.
Okay, that handles the immediate physical collision avoidance, but what about the strategic safety? How does it avoid those reserved areas or known enemy threat zones without the network?
That's where the procedural knowledge is maintained, but only as a contingency. The system integrates a PACE plan. Primary is dynamic integration. If connectivity is lost, that's the emergency condition, and all air platforms automatically revert to pre-briefed safe state procedures.
So they would instantly climb or descend to a pre-designated bailout altitude.
Right. And in doing so, they temporarily recreate a rigid procedural corridor until communications can be restored.
So we only revert to static procedures when the technology fails completely, and only for as long as we have to.
Exactly. And that's the huge difference between a distributed resilient mesh that defaults to local sensing versus our current system, which relies on a centralized COC that, if targeted, instantly blinds the entire force.
The centralized ACO is a single point of failure.
Whereas the mesh, with its PACE plan, is actually designed for degraded operations.
Okay, now for the spoof scenario. This is the high-tech cyber threat. What if an enemy hacks the network and injects false data? A ghost artillery barrage or phantom enemy aircraft tracks designed to deny us key airspace or mask their own movements.
This is countered by what the paper calls the hierarchy of truth, and it's built on a zero-trust architecture. The philosophy is actually very simple. Local physics always overrides remote data. You trust your own senses first.
Let's walk through the specific failure mode here. Scenario A, the ghost wall.
Okay. A hacked node in the network starts broadcasting a massive, mandatory keep-out zone right on the pilot's optimal flight path. It's claiming there is a heavy, friendly artillery barrage underway. The system is telling the pilot, turn back, danger is high.
Okay, but the pilot's own sensors are scanning that area.
Right. The aircraft's organic sensors, its thermal imaging, its onboard radar, they scan that exact volume of airspace and detect zero ballistic signatures. No heat plumes, no fast-moving objects, no detectable electromagnetic energy coming from the supposed firing platforms.
So how does the hierarchy of truth resolve that contradiction?
The algorithm weighs the onboard sensors, the pilot's eyes, higher than the remote network map data. It flags the network data as an anomaly, a potential spoof, and it downgrades the risk from prohibited to something like caution or advisory.
And then the pilot is allowed to proceed relying on their own sensors.
Exactly. It prevents the enemy from using false data to procedurally anchor our own operations from within our own network.
That is a fundamental paradigm shift. I mean, pilots are trained to follow the GPS, to follow the map. But here, the system is programmed to sometimes ignore the network instructions if they contradict local reality.
It has to. Now consider the opposite. Scenario B, the hidden threat. This time, the network reports all clear. It's giving the pilot the green light to proceed. But their onboard sensors suddenly detect a newly activated enemy radar lock or a heat plume from a hidden anti-aircraft unit that the network hasn't registered yet.
So in this case, the local sensors detect a real risk where the network is promising safety.
The decision is immediate evasion. The platform's survival instinct, its own organic threat detection capabilities, will always override the network's permission or reassurance. This ensures that even if the network is partially degraded or operating slowly, the individual platform maintains its own survival capability based on instantaneous physics.
And to prevent the enemy from injecting this bad data in the first place, how is data trust maintained across this massive mesh network?
It's done through cryptographic provenance. Every single piece of telemetry data, every data bullet transmitted across the mesh, carries a cryptographic signature that verifies the sender's authenticity and integrity. The system doesn't just trust a signal because it's fast. It verifies the source, ensuring that the critical geometric data used for deconfliction is authentic and hasn't been tampered with.
The counterintuitive truth here seems to be that a dynamic, decentralized system, even with these potential cyber vulnerabilities, is still far safer than the existing static system.
Because the existing static system is essentially an open book. It's already compromised by its sheer predictability.
We are broadcasting our intentions and our operational boundaries every single time we write a static ACM.
A dynamic system, while it might be vulnerable to sophisticated cyber threats, is much harder to target because its intentions are fluid and its decision-making is distributed across thousands of nodes.
This moves us to the final, and I think maybe the hardest hurdle of all, the necessary cultural shift. We are asking senior commanders and staff officers to abandon decades of deeply ingrained habits that are rooted in human verification and this idea of positive control.
It really requires the modern military organization to accept systems over permission. We have to be willing to transfer risk from the fallible, slow human to the statistically reliable, instantaneous algorithm.
So we have to move past this obsession with a human having positive control and instead embrace actuarial security. The proven statistical reliability of a validated system that operates at machine speed.
That is the leap of faith, and it has to be backed by rigorous testing and science. We just have to acknowledge that a human ground liaison officer trying to interpret a 4-hour-old map and issue verbal clearance over a radio is, statistically, a greater risk to the pilot than an AI-enabled deconfliction system operating with verified, real-time data.
The human element, constrained by time and cognitive capacity, is the vulnerability we're trying to mitigate.
It is the single biggest vulnerability.
And this cultural shift is what allows us to finally dominate the staff fight, that competition of processing speeds, which is ultimately the fight for OODA-loop dominance.
If our staff takes 24 hours to write and disseminate a new static airspace control order, and the enemy is capable of changing their force disposition and identifying our vulnerability in 6 hours, we are perpetually operating inside their reaction cycle.
We're losing the OODA-loop observe, orient, decide, act before we even start the fight.
Every time. By offloading the constant, painstaking work of deconfliction and geometry management to the edge algorithms, we're essentially automating the minutia of staff work.
And that frees up the joint staff, the high-level strategists and commanders, to focus entirely on high-level strategy and intent.
Exactly. They are no longer bogged down in the geometric details of where every single plane and shell is going to be second by second. They can focus on the why and what we are trying to achieve, while the systems focus on the real-time how.
So when you put it all together, what does this all mean for the future of warfighting? The choice presented in this paper it's profound.
The choice is incredibly stark. We can continue to control the airspace using static procedures until we lose the war due to our predictability and our temporal lag. Or we can fully integrate the airspace dynamically and dominate the fight through speed and resilience.
We're really beyond the luxury of having unchallenged air superiority.
We can't just muscle our way through future conflicts using static management that actively broadcasts our intentions to a peer adversary. It's suicidal.
So let's just synthesize the core requirements one last time. This whole concept requires building a resilient network where all systems, from the lowest artillery shell to the highest fighter jet, can see, talk, and adjust instantly.
And in doing so, we move beyond the archaic process of drawing lines on maps and waiting for a human to give their approval.
And that is the core requirement for building a joint force that is fiscally sustainable, technologically superior, and most importantly, agile enough to survive and dominate pure combat in a contested domain.
Let's review the 3 major shifts that really define this transition into the algorithmic sky.
First is that fundamental change from static procedural management, that slow, fragile BBC broadcast model we talked about, to dynamic algorithmic integration that allows real-time, instantaneous negotiation of the battlespace geometry.
Second is the necessary transfer of burden. We're moving from slow, fallible human cognitive processing, the pilot as a data processor, to instantaneous machine geometry processing, which is constantly verified by onboard organic sensing.
And third, the huge shift from centralized permission, which creates that single point of failure at the CAOC, to decentralized edge resilience, backed by mesh networking and that critical safeguard of the hierarchy of truth.
That's a phenomenal amount of strategic and cultural change, and it's all driven by the simple necessity of speed.
It is. But this raises one final provocative thought for you to mull over. If this concept, this digital VFR, which prioritizes local sensor data over centralized network instruction, all backed by cryptographic provenance, if it succeeds in making military airspace safer and more lethal, what elements of this revolutionary approach could radically change civilian infrastructure?
That's a huge question.
Imagine civilian air traffic control moving to a mesh network with edge deconfliction between airliners, or even infrastructure management in hyper-complex urban environments where autonomous public transportation systems use cryptographic provenance and local LiDAR data to override centralized grid instructions during an emergency.
The foundational challenge posed by this military concept, which is the need to distribute trust and decision-making to the edge, it really does have ramifications for almost every centrally controlled system we rely on today. It challenges the very definition of security and efficiency.
Indeed. We've certainly given you a new framework for viewing the skies and the software that controls them. Thank you for joining us on this deep dive into the algorithmic sky.
Thank you for listening.
We'll see you next time.